We will continue our discussion on vibration of rigid bodies. Last lecture I discussed about bifilar suspension. Now we discuss a case of tri-filar suspension. Sometimes it is convenient to find the moment of inertia of a disc by observing the frequency of oscillation. When the disc is suspended by 3 wires symmetrically about the axis of the disc, then that is called tri-filar suspension. This arrangement is shown here in this figure. We can find out the moment of inertia of the disc by seeing its oscillations. The force balance gives T is equal to 1 by 3 W. Disc is acted by a gravity force W, and there is a tension T in the strings is 1 by 3 W. W is the weight of the disc. Now this is, we can provide a small twisting in this plane of the disc. That means disc remains its own plane, but this point radius moves to another point, that is theta, and therefore these strings get the inclined. So this is at this point, this is this point, this is this point, so this is phi. Now therefore r theta is equal to L phi. In this case you can see r theta will be equal to L phi. L is the length of this thing, so r theta is equal to L phi, where r is the radius of the disc and L is the length of the string. For very small rotation theta, and hence if theta is small, then phi is also small, the tension will still be T, no change in the tension. Then the horizontal component of the tension is equal to T phi. Actually it is T sin phi, but sin phi becomes equal to phi. So that is equal to 1 by 3 W r theta by L. There are 3 wires and horizontal components produce restoring torque. Therefore restoring torque is equal to minus 3 T phi times R. So this is 3T phi into R. So that is minus W by L. This is R square theta. Now by D'Alembert's principle, inertia torque equal to minus I alpha, and that must be that, and restoring torque together should keep the body in equilibrium. The body is in equilibrium under the action of these torques. That means I alpha plus W by L R square theta, that is equal to this one. Now here this is actually, instead of I alpha, this is basically I theta. This is thing that it is I theta. Let us see that here. Okay. I theta, if I say that theta, disc rotates by theta, and this is W by L this is r square. Now this is the W by I theta, inertia torque is I theta double dot like this. Okay, theta dot. There you know that theta double dot is basically same as angular acceleration alpha. So therefore this is the difference in the notation. So this is alpha is equal to theta dot like this, and this is equal to, this is basically I alpha can be written as W by G K square alpha, because I is equal to W by J K square, and plus you add here W by L. This is 3T here also, it is must be 3 W by L R square, and this is theta. This is theta double dot. Okay, so this is, so basically you get equation like this: W L by, okay, but this is 3W, this is W only because T was W by 3, so this is W, so this is correct. So this is W by L R square theta plus W by G K square theta double dot is equal to 0, and this is, compare this with mx double dot plus kx is equal to 0. So it is basically the same way that W gets cancelled, it becomes R square G L K square. So this is R square by L and G by K square. Thus by measuring the natural frequency, the radius of gyration K, and hence I can be estimated. So we can find out, so if you measure the natural frequency omega n, you know the gravitational constant, you can find out its R, and you can find out, this is the thing, L is known, so one can find out this thing. Now till now we have talked about the free vibration problems. Now let us go to the forced vibration problem. An example of a forced vibration of a rigid rod is like this. This rod is hinged at this point, and an excitation force F0 sin omega t is provided at point A, and dash part is at a distance of B. This distance is L. This is the spring. Here spring stiffness is K. This is A. This is B. Now this is the D. So this is a dash part, linear dash part. Here OA is a rigid rod hinged at O. There is a spring attached at a distance of A from the hinge, and the dash part at a distance B from the hinge point. So dash part is that. For small theta, the equilibrium equation is ml square by 3 theta double dot plus ka square theta. ml square by 3 is the mass moment of inertia of the rod, cylinder rod about point O. Mass moment of inertia of an uniform rod about the center of mass is ml square by 12. About its one end, it is actually ml square by this thing, because apply the parallel axis theorem, ml square by 12 plus m into L by 2, distance is L by 2, L square by 4. So this is 3 L square by, so therefore this is ml square by 3. For small theta, the equilibrium equation is ml square by 3 theta double dot plus ka square theta, that is the restoring force due to spring when you displace it by theta, this spring gets stretched by a theta. So k times a theta is the force, and force in it acts at a distance a from the hinge. So k square theta, k square theta. Similarly, the dash part is moving. So b theta is the displacement of the dash part, b theta dot is the velocity, and therefore the force is equal to c times b theta dot, but it is acting at a distance of b. So therefore it becomes cb square theta dot, and this is equal to f0 sine omega t multiplied by L. L is the distance from here. So this is, therefore you get W by G by L. This will be ml square by 3 theta dot, and this becomes this is this one. Okay, there is no need to write this equation, f0 sine omega t into L. So actually compare this equation. Now compare this equation with equation x double dot plus k by m x plus c by m x dot is equal to f0 sine omega t by m, which was that spring mass and dash part system. So by this you can find out. So here omega n is equal to natural undamped frequency omega n is equal to under root 3 Ka square divided by ml square, and damping factor zeta is equal to 3cb square divided by 2m L square omega n, and omega d is equal to omega n under root 1 minus zeta square. So therefore, okay, f0 theta dot, so this is equal to this one. Now omega n is equal to square root 3k square by ml square. This is zeta equal to 3cb square divided by 2 ml square omega n, and omega d is equal to omega n under root 1 minus, this is tau square. The particular solution of this is theta is equal to a cos omega t minus phi, where phi is equal to tan inverse 2 zeta omega by omega n divided by 1 minus omega by omega n whole square, and a is equal to 3 f0 by L k square. This is 1 minus omega by omega n whole square. This is whole square plus 2 zeta omega by omega n whole square. This is 1 by 2. Now let us discuss another problem, vibration of a rolling cylinder. A cylinder kind, when it rolls on the that in a straight line, it is having, if it is a pure rolling motion, then there is only 1 degree of freedom, because its r because its angular displacement and the displacement of the center are related. R into theta is equal to the displacement of the center. However, if it is not a pure rolling motion, if there is some slipping, then you know this type of thing is not correct. That means there is no relation between the velocity of the center and the angular velocity, and we cannot, suppose you give the angular displacement of the cylinder, we can't know that how much c has moved because there is some slippage. So therefore 1 degree of freedom is not enough, you have to have 2 degree of freedom. So therefore we discuss the case of that motion in which the cylinder rolls without slipping. It is, this cylinder is held by spring, this is the spring and this is the thing, and it is attached at the center, and now it is displaced slightly. Now make the free body diagram of the cylinder which is shown here. We isolate the cylinder, make the free body diagram. What are the forces? Let us discuss the forces coming on the center. One is the spring force, restoring force of the spring. When the cylinder center has moved at a distance by distance x, then the spring gets stretched by amount kx. So kx is the force of the restoring force of the spring. W is the weight of the cylinder, acts downward. N is the vertical reaction of the floor, and F is the force due to friction. So we have got these four forces: spring force kx, friction force F, normal reaction N, and weight W. Now we have to N, if there is no vertical motion, then N must be equal to W, but then there is a horizontal direction, there is motion. So equation of motion in x direction is minus F minus kx is equal to mx double dot. There, because F is the friction force which we don't know at yet, but we have to write equation minus F minus k. Now if you apply the angular momentum equation about the geometric axis of the cylinder at O using theta to measure the rotation of the cylinder, if you say using theta about this one, so therefore it is F into R is equal to 1 by 2 mr square theta. Now if you take about the geometric axis, when you take the moment about this point, kx will not produce any moment because it is passing through O, W will not produce, N will not, only F will produce a moment, and that magnitude is given as F into R, and that is equal to half mr square theta, because if it is a solid cylinder, its moment of inertia is half mr square. Otherwise it is a hollow cylinder, then it is can be mr square theta. I for the cylinder is half mr square, where m is the mass and r is the radius. Now as there is no slip, we can write that equation x double dot is equal to r theta double dot. That is the linear acceleration is equal to r times the angular acceleration. Therefore F into R is equal to half mr square into x double dot by R, and therefore F is equal to half m x double dot. Now substituting for F, we have mx double dot is equal to minus half m x double dot minus kx, and therefore x double dot plus 2 by 3 m x equal to 0. This is the thing, because here this will be 3 by 2 m x double dot plus kx equal to 0. Compare this equation with the spring mass system, where we had mx double dot plus kx equal to 0. Here we are having 3 by 2 mx double dot plus kx. So therefore effective mass is actually more. This is, so therefore x double dot plus 2 by 3 km plus x equal to 0. This is the differential equation of the motion of a cylinder held by the spring. There is one alternate way to obtain this differential equation. In this, we draw the free body diagram like this, but we take the A is the instantaneous center of rotation, so we take the moment about this fixed point of contact. About this point, that mass moment of inertia is equal to half mr square plus mr square using parallel axis theorem, because the mass moment of inertia about the center of the cylinder is mr square. Now in that you add half mr square, and this is theta double dot is equal to minus kx times r. Now theta double dot is equal to minus x double dot by r, as it is a pure rolling motion. In pure rolling motion, angular acceleration and linear acceleration of the center are related. So this is minus 3 by 2 mr square x double dot by r is equal to kx by r. Therefore, x double dot plus 2 by 3 k by m x equal to 0. So we get the same type of differential equation. Now this differential equation can be solved. Solving this differential equation, omega will be naturally under root 2 by 3 k by m, x0 cos under root 2 by 3 by mt plus x double dot 0 under root 2 by 3 k by m sin under root 2 by 3 k by m. T is outside the square root sign. x0 and x dot 0 are the initial position and speed of the center of the mass. Theta is equal to x by r. Now theta is equal to, so therefore theta is equal to x by r. So we put in terms of that, theta is equal to x0 by r cos under root this one. Similarly here you put x0 x dot 0 r under root 2 by 3 km sin under root 2 by 3 r by mt. Natural frequency of the cylinder is 2 by 3. This is k by m. So this is the motion of that cylinder. So this one, it is about this one. So we have explained about this. Now we have discussed these problems. Now let us go to the another problem of that we can solve the vibration problems by another method, by energy method. That portion also we will discuss here. We know that in the conservative system the total energy is constant and the differential equation of motion can be established by the principle of conservation of energy. For the free vibration of an undamped system, the energy is partly kinetic and partly potential. The kinetic energy T is stored in the mass by virtue of its velocity, whereas the potential energy is stored in the form of strain energy in elastic deformation or work done in a force field such as gravity. You can have a spring mass system where the strain energy is stored in the spring, and we can have that simple pendulum where the energy is stored in the force field like gravity. Now total energy is always constant in the free vibration, therefore the rate of change is 0. Now therefore what happens, we can write this equation T plus U equal to constant in a free vibration. T is the kinetic energy, U is the this one, and it is this one, this means that basically d by dt t plus u equal to 0. That means if we take the derivative with respect to time, you should get 0. Although in the kinetic energy you get the velocity term which may be function of time, and in the potential energy you get displacement which is also function of time. If our interest is only in the natural frequency of the system, it can be determined like this. From the principle of conservation of energy, we can write for two instants T1 plus U1 is equal to T2 plus U2. T2 plus U2. Where 1 and 2 subscript represent two instances of time. Let 1 be the time when the mass is passing through its static equilibrium position, and choose U1 equal to 0 as reference for the potential energy. You know, kinetic energy is 0 when the velocity is 0, but for potential energy there is no such a rule that when the displacement is 0 then potential energy is 0. You have to take a datum. With respect to that datum, you measure the change in potential energy. So therefore, let us say that when U1 equal to 0 as the reference for the potential energy, that means U1 equal to 0 at equilibrium position, and T2 be the time corresponding to the maximum displacement of the mass. At this position, the velocity of the mass is 0 because extreme position, that is the maximum displacement has occurred. It cannot go beyond that. So velocity must be 0, otherwise it will go in that direction. So T2 is equal to 0. So therefore T2 is also 0. So you have a relation, then T1 plus 0 is equal to 0 plus U1, or we have got like this: T1 is equal to, this is U2, this is U2, so this is T1 is equal to U2. If this system is undergoing harmonic motion, then T1 and U1 are of maximum value. That means at the center T1 will be maximum when the potential energy is this one 0. So obviously that T1 is maximum, and then here U2 is of maximum, therefore T max is equal to U max. U max. Therefore, for a spring mass system, now let us see for a spring mass system how you can apply this condition. Now T is equal to half m x dot square. At any instant, its kinetic energy is given by half mx dot square, and u is equal to half kx square. Now it is t plus u is constant, so therefore half mx dot square plus half kx square d by dt is equal to m x dot x double dot differentiate it plus kx x dot equal to 0, or so you get the equation m x dot double dot x dot plus kx dot equal to 0. Okay, so therefore we get a differential equation mx dot double dot plus kx equal to 0. Okay, so this is because x dot is can be eliminated except at the extreme position where x dot is equal to that 0. So therefore you get that differential equation, that is mx double dot plus kx is equal to 0, and so this differential equation is equal to like this, and this is only now for finding out the natural frequency. Let us assume that x is equal to a sin omega t. If you assume that x is equal to a sin omega t, then we get t is equal to half a omega cos omega t whole square multiplied by m. As the maximum value of cos omega t is 1, therefore t max is equal to half a omega square into m is equal to half m a square omega square. Similarly, the potential energy is given by U is equal to half k a sin omega t whole square. As the maximum value of sin omega t is 1, therefore maximum potential energy U max will be half k a square. Maximum value is half k a square. Now T max is equal to U max, therefore half m a square omega square is equal to half k a square. Now from this equation we get omega is equal to under root k by m, which is the expression for the natural frequency. So therefore you get omega is equal to under root k by m. Now so like that we can find out. Now let us, in the last lecture we have solved one problem, vibration problem of this. This is the cylinder which rolls without slipping on this thing K, and this is the mass M. Now it is a cylinder which rolls without slipping and is held by spring. The total energy of the system is given by, total energy is half mv square. So let me write the expression here, half mv square plus half I omega square plus half kx square is equal to constant. Total energy remains constant. Now in this case this can be written as half m x dot whole square plus half I x dot by r whole square plus half k x square. if you differentiate this equation for total energy with respect to time, you get mx double dot plus I r square x dot plus kx equal to 0. Note that here we could write omega is equal to x dot by r because of the rolling motion. So this is pure rolling motion. So this is like that. So omega is equal to under root now k divided by m plus I by r square. You get this term. Now for a solid cylinder, I is equal to half mr square. For a solid cylinder, I is equal to half m r square. Therefore, omega is equal to under root 2 by 3 km. That is the same expression we have got. This is the type of that thing. Let us take another example on the use of the energy method. Here, if we have got a concave surface like this, now here you have kept a ball just like that. Now displace it slightly here this side, so it goes like this here. Then its potential energy increases. You reach it at this point, it tries to come back, but by that time it has attained velocity, it will go on the other side. Neglect the friction, you will see that this goes this side, then again it tries to come, and like that it keeps oscillating. Here it goes, attains the maximum velocity, after that comes back, and after that goes in this direction, again its velocity becomes 0, and this is what that this thing is there. Then this is theta, 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 this is r. Now if the maximum angle it is theta, and cylinder, that increase in the height of the center of the cylinder is basically r minus r 1 minus cos theta. That is the increase in the height of the center of the cylinder. Cylinder is of radius r, so this distance is r minus r. Therefore, this is r minus r into 1 minus cos theta. Assume that the potential energy at the equilibrium position in the middle is 0. So maximum potential energy is U max is equal to mg r minus r into 1 minus cos theta. Theta is the angular amplitude type thing. Now here, if we assume that theta is small, then cos theta can be written as, 1 minus, expression for cos theta is 1 minus theta square by 2 plus other terms. Okay, that this one, but where theta is in radian, therefore 1 minus cos theta is theta square by 2. Therefore U max is equal to mg r minus r divided by 2 theta square for small theta. Now for small rotation, the velocity of the mass center is Vc is equal to r minus r theta dot small rotation. Now let the angle of rotation of the cylinder is phi, then r minus r into theta, that is the moment of the center, is equal to r phi, where phi is the angle of rotation of the cylinder about its own center. So therefore phi is equal to r phi, therefore phi is equal to r minus r divided by r theta. Hence the angular velocity of the cylinder is equal to omega r minus r divided by r into theta dot. Or else see it like this, that there is a cylinder, this is r, and this was moved by some distance, center moves r minus r into theta, and therefore if about instantaneous center, if you see the distance, so it is r, so therefore omega is equal to r minus r by r theta dot. Therefore the total kinetic energy of the cylinder is equal to half m Vc square plus half I omega square is equal to half m r minus r square theta dot square plus half m r square r minus r square by r square theta dot square, which is equal to 3/2 m r minus r square theta dot square. Total kinetic energy of the cylinder is half mvc square plus half I omega square, which we got 3/2 m r minus r square theta dot square, and total energy comes out to be 3/2 total energy 3/2 m r minus r square theta dot square plus mg r minus r theta square by 2 is equal to constant. Differentiate this expression with time. This must be 0, that means 3/2 m r minus r square 2 theta double dot theta plus mg r minus r by 2 theta dot equal to 0 r theta dot plus 2g divided by r minus r into theta equal to 0. Compare it with mx dot double dot plus kx equal to 0. We see that omega n is equal to under root g divided by 3/2 r minus r. So we get this type of expression, and that is about this one. If R is equal to infinite, that means that it is a plane surface, then there is no vibration, that is by this one. And if R is equal to in a state that if this is just a ball, if a point mass particle is there, then it will be G by 3 by 2 R minus R. So this is the thing. So this is the velocity of that mass. And now let us take another example. Next point is like this. Okay, now this will be, yes, if you take a rod and here there is a spring attached here K, and this is a spring is attached on this side as well. This is K, this is K, this is P, this is L. Let a rod of mass M and length L is restrained in the vertical position by two identical springs having spring constant K. A vertical load P acts on the top of the rod. So this is acting. If given a small displacement theta to the rod, one spring compresses by amount L theta. If you just give a displacement here theta, so this is, I am showing very exaggerated theta, so this is L theta, and the other spring stretches by the same amount, that is this one. So strain energy in the spring is equal to 2 half K L square theta square, because this is the thing, that is K L square theta square. And when it moves, rod moves like this, then the center of the gravity of the rod mass moves by L by 2 1 minus cos theta. That means again that is L by 2 into theta square by 2, provided theta is very, very small. So therefore the potential energy of the rod changes, and potential energy change due to this is given by potential energy change is equal to minus m L by 4 theta square. Now when this is due to that this one, but this force AP which is acting, that also gets displaced, that also comes down. So potential energy change due to load P is PL, because this is PL P into this is L 1 minus cos theta, or this is PL by 2 theta square. Now if we go to that like this, So kinetic energy of the rod is equal to half m L by 2 theta square plus 1 by 2 ml square theta dot square, or that basically it will come L square by 4, and this is 1 by 12. So it is I theta square, because this is like this. So this will become equal to half m this is L square by 12, and this is 4. So this is you can take 4 common, and this becomes basically L square ml square by 12, and this is 3 plus 1 4. So 4 ml square by 12 theta dot square, or ml square by 3 theta dot square into half 4 ml square. So this is half is there, this is half ml. So this is equal to half is equal to half m L cube by 3 theta dot square. Therefore total energy is equal to ml square by 6 theta dot square plus KL square minus PL by 2 minus ML by 4 theta square. Okay, this is total energy previous 2 by 3. Okay, this is the thing. Total energy is equal to, this is equal to, this is the expression theta is, this is theta square. That means, let me write it again. Total energy is ml square by 6 theta dot square plus KL square minus PL by 2 minus ML by 4 theta square. Now differentiate, this is equal to constant. So differentiate it with respect to time. This expression can be differentiated with respect to time, and then you get 0 is equal to ml square by 6 2 theta dot theta double dot plus KL square minus PL by 2 minus ML by 4 2 theta dot theta. So therefore theta dot can be cancelled throughout. Therefore you get ml square by 6 theta double dot plus KL square minus PL by 2 minus ML by 4 theta is equal to 0. Now observe this expression that you have written ml square by 6 theta double dot plus kl square minus pl by 2 minus ml by. Compare this expression with mx dot plus kx equal to 0. When you compare this expression, you notice that this was positive. Then only we got this thing k is positive. Therefore, this expression in the parenthesis must also be positive. Then only the system will vibrate. If the expression is not positive, then the system will not be vibrating about this thing. Therefore, that is the condition for this, is that this expression must be this one. Then it will be vibrating and restoring force will be able to bring to original position. However, if you go on increasing P, then you can say this expression PL by 2 KL square minus, because that expression, pay attention to this expression, KL square minus PL by 2 minus ML by 4. What happens if this expression is less than 0? Less than 0, what happens? P, if we increase P, what will happen? So in that case, there will be a value of P at which this expression will become negative. Beyond that, if you put that also, so at that point it will be unstable. The rod will not be able to come back. When you displace it, it will go in the other direction. Exactly when KL square minus PL by 2 minus ML by 4 equal to 0, at that point you can give any displacement, the rod will remain at that position. It will not try to come back. Therefore, the condition is that from that, so this P can be called critical load. Critical load at which this will become unstable. There will not be any vibrations, but this is the thing. And if P is more than that, naturally that it will have tendency to go to the other direction, and therefore the critical load is KL square minus PL by 2 minus ML by 4 equal to 0, or P is equal to KL square 2KL square 2KL, that is minus M by 4. So at that point, this rod will try to come back to that original position, and this is what that means. If P is less than 2KL minus M by 4, the rod will try to come back to the previous position, and this is how that we have obtained the expression for that vibration, and this will be this thing. So here, that to summarize what we have done, that we have shown that there is another approach to obtain the differential equation of motion, that is not by solving the system force balance, but by the energy consideration. In the free vibration case, total energy of the system remains constant. So therefore, by that consideration, we have obtained these expressions, and we can find out the angular speed. So that is the another way of solving the vibration equation. It becomes many cases, this system becomes very simple. Let us quickly do that one more problem and then conclude this thing. Supposing you have the vibration of this rod M, and this is Kx, K1, this is K2, K2. Then if you say put kinetic energy T is equal to half m x dot square, then U is equal to half k1 plus k2 x square, because half k1 x square energy is stored in both, and therefore half mx dot square plus half k1 plus k2 x square is equal to t plus u, that is constant. Differentiate it with respect to time, you get mx dot x dot plus k1 plus k2 x to x dot is equal to 0. So you get the differential equation as mx dot plus k1 plus k2 into x is equal to 0, and in this case, so this is the equation of this one question. If we quickly want to find out the frequency, we can always put x is equal to a sin omega t, and then we can find out, put x dot, so therefore, and then by equating t max is equal to u max, we can find out the expression for that angular omega, that means circular frequency. So this is the thing. So now, okay, so therefore I will stop at this point.